Okay, so good morning to everybody. And this talk will be about a model developed many years ago, by some 20 years ago, by Paolo Papale and myself with Giulio Tonello, and it's about degassing, the solubility and degassing of water, carbon dioxide, sulfur dioxide, and hydrogen sulfide. Well, later the model was named CHOSETTO because it's about a major species in the CHOS silicate melt systems. Actually, it combines three main models. One is the equation of state for the fluid phase provided in 1992 by the Saxena group in Uppsala, so the superfluid equation of state. The other model is the famous Papale et al. Model for solubility of water and carbon dioxide in silicate melts. And the third one is well, the sulfur solubility model, the polymeric model by Giulio Tonello and myself, which also includes the oxidation state, iron and sulfur oxidation state. So actually, and this is something that should be generalized to all the so-called models, this is a method rather than a model. Anyway, this method provides a quite high degree of internal consistency. Our main concern was to have all these modules to reason, to share information each other, to solve mass balances, which is actually quite an easy numerical problem. And well, we hope to have achieved this goal, but of course, this is a multi-component system, and sometimes there are, that's probably the major point, some problems which are actually purely numerical. But well, it's an uneasy task that any model actually has to deal with it. Anyway, the famous Papale et al. Model, it's well, pretty celebrated for its capability to deal with non-linear behavior, in particular, to treat the activity coefficients of H2O and CO2 in the silicate melt. And those non-linear behaviors have sometimes also quite unexpected features, depending, of course, on the melt compositions, such as, for example, if you look at the uppermost right panel, some kind of maximum in the CO2 solubility compared to water solubility when you plot the saturation isobars. But however, this behavior can't be found, of course, in ideal or pretty ideal model. And it is, of course, a source of major uncertainty, especially when these models are inverted, are used to, of course, calculate pressure depth of gaseous solution, for example, from a magma chamber. Anyway, these non-linearities are not only, of course, numerical solutions of a model, but they are also sometimes they reflect the physical reality. This study, for example, coming from Tamic et al. In 2001, actually reproduce this feature, but I have also to tell you that the feature was already present in an early Papale model in 1999. So actually, the model in its exploration of the pressure, temperature, composition domain has revealed some features which later on were found experimentally by other coworkers. And the 2006 version has actually updated the database and also included much better CO2 coefficients because CO2 solubility was modeled also considering the role of iron partitioning between divalent and trivalent iron in the silicate melt. So this model can be found online, for example, as a web calculator, can be found, it's easy when you work with the two volatile components, much easier than three volatile components. Anyway, the model is implemented, for example, in as a web calculator by INGV, the PISA branch of INGV, and you can easily access, or there you can also download a Fortran version. All these models that we have done are based on old Fortran 77, which is probably a little bit old-fashioned, I understand. But anyway, it does the job and can be used, for example, to compute H2O, CO2 degassing, or calculate the saturation pressure. Just let me stress on the importance of having a good consistency in modeling the solubility joined with oxidation states. Even if you are not considering yet sulfur, but simply because the CO2 solubility is widely dependent, importantly dependent on the oxidation state. This is just an example recently published about Soufrière de Guadeloupe, andesite, and Etna basalt. And you see that, well, unexpected non-linear behavior appear even if the total volatile amount in the system, water and carbon dioxide, is the same, temperature is the same, but the saturation pressure depends strongly on the oxidation state, on the partitioning of iron between divalent and trivalent. And the effects, at least those that can be computed via the model, can be important. And this has, of course, huge implications in volcanology. Iron, just a few words on the iron oxidation state. The iron oxidation state in silicate melts is, well, for some times has been a difficult task because its activity coefficient are highly non-linear dependent on melt composition. Everybody knows that if you span over a wide range of melt composition, finding a simple, when I say simple, I mean by using regular solution models or sub-regular solution models, finding a simple expression to fit activity coefficients of FeO and F2O3 in silicate melts is a very uneasy task. You can't cover with that kind of expression, even if they have a thermodynamic meaning, you can't cover the values which have been found experimentally in all the silicate melt compositional spectrum from basic to acidic to rhyolitic. The point that we have realized many years ago, and this is actually at the core of our modeling, is the so-called amphoteric behavior of iron. Briefly, trivalent iron can be either network former or network modifier. From the point of view of acid-base chemistry in a strange solvent, which is the silicate melt, from the point of view of acid-base chemistry, this implies amphoteric behavior. So it happens that this double dual behavior exists, and so we must deal with it, and we must introduce this behavior, which means actually solving for one more chemical equations. And when we do that, actually we are able to fit the oxidation state of iron in a wide spectrum of silicate melts. Let me just tell you that the model, because, and this is also another element contributing to internal consistency, includes water speciation. Water speciation, again, it's about the amphoteric behavior of water. There is a strong role played by basic dissociation of water, not only acidic dissociation. This has an effect, a strong effect on the polymeric properties, then it has a strong effect on the redox properties. Let's say that saturation properties of volatile components, redox properties of iron, sulfur, and all the multivalent elements that you want to look at, and acid-base properties are all related because of the polymerization, because of the structure of silicate melts. It's uneasy to find the rule of thumb of all of this, and we should avoid too detailed description that sometimes are useless, but it's like acid-base chemistry in aqueous solution. Just to give you a sharp example, we don't need to know in detail the structure of liquid water. Nobody knows the structure of liquid waters, but we need to assess the acid-base properties of water. And this is actually what we have to do. We still have to do for silicate melts. And I mean, it's about chemistry. So we try to pursue this way. We try to follow this approach. Results are, in our opinion, are not so bad, even if they may appear complicated in terms of approach. I mean, it's not only push the button and find the solution. And sulfur, then it was, in our opinion, approached in this way and also solved in this way. Now it's just a matter of calibrating the database, because our last calibration dates back to 2006, 2005 actually. So now there are 17, 18 more years of data, and it would be nice to treat them. And we are going to do that also because we have a project about that. And so sulfide and sulfate capacities of silicate melts were actually assessed based on this polymeric approach, which means computing the different species of oxygen in silicate melts. This is actually the core of the acid-based approach. And so this is the set of equations. I don't want to enter into details for sulfide capacity. By the way, when you follow this approach, you realize that there is no difference between simple binaries and multi-component silicate melts. Simple binaries are even most difficult, the most difficult ones, because the energetic difference between the silica and the other oxide can be exacerbated, whilst in a silicate melt of 10 components, like geological melts, you are actually in a narrow polymerization range, polymerization domain, and everything is somehow averaged. So first of all, we must be able to solve simple systems like binaries. And we do that, we have done for several systems from metallurgy and geology appearing in the literature. The approach is also applies also to sulfate capacity. What we have in this model is actually the combination of solubility of sulfide and solubility of sulfur as sulfide, solubility of sulfur as sulfate. But if we have both, depending on composition, we have also implicitly, this slide is just to show you that later on some results were confirmed also experimentally. If we have that, we have implicitly also the redox dependence of sulfur on silicate melt composition. Because I mean, it's even automatic, logical. If you solve the solubility of sulfur as sulfide, depending on composition, and you solve the solubility of sulfur as sulfate, depending on composition, when you put both of them together and you make the ratio, you have the oxidation state of sulfur depending on composition. I mean, it's I would say normal, implicit. And the model actually does this. And for example, we can, like in this slide, solve for some interesting compositional dependencies of the oxidation state, for example, ethanol volcanics, depending on water. Again, water, because of its effects on melt polymerization, it affects the oxidation state of iron and, of course, of sulfur. And vice versa, the redox state will affect the solubility of water. So all these things must be computed somehow internally consistent. And I repeat, sometimes numerical is not very easy. We have also made an implementation for sulfide saturation. We have a lot of work to do to make all this user-friendly. That's the point. And hopefully this will be done soon. This is the major issue, to provide some kind of tool, push the button, find the solution. But everything must be behind this. So this is the final model. Now I'll show you just a couple of results very, very quickly, I promise. And the description is more or less based on the separate modules I gave you so far. Some behaviors that can be found in the literature are simply because of, in our opinion, of the effects that we have described so far, in particular, the solubility minimum of sulfur. It's the only, I would say, linear behavior which can emerge if you remember, for example, that you must plot the sulfur concentration in the melt in a log form normalized by the fugacity of a sulfur species. Otherwise you can see that. And what else? Remember this connection, because it's about well, basic chemistry in every solvent, water, organic solvents, silicate melts as well, acid-based properties, polymerization, redox properties. The model, now I'll show you just a few results, can be found, I contributed to the GitHub web page by Charles Lelosque at IPGP in Paris. But you can also find, which is probably more important, the separate modules. So if you want, you can take them and combine and solve on your own mass balances by combining the different modules. So not necessarily you have to follow our numerical strategy, which sometimes is, I repeat, very hostile. Some results can be found in this publication, some better description. And the numerical problem, let me tell you what I mean. Imagine that this is the saturation line, the horizontal black line. If you deal with water and CO2, everything works good. If you introduce a third component, the orange is sulfur, well, if I would say is connection to the total solubility of all volatiles is quite sharp, abrupt, then numerically we have no problem. And this applies for reduced sulfur. When you move to oxidized sulfur, in this region, in which you have to solve actually the very slight, the very tiny inception, the very small beginning of sulfuric solution, when it's oxidized, actually this is the shape. Well, this is a very numerically unstable area. It's very difficult to find the solution for this behavior about oxidized sulfur together with water and carbon dioxide. Things are different for reduced sulfur, and this can be a numerical problem. So my personal suggestion, for example, is if you want to calculate pressure, just use the Papale model for water and carbon dioxide, forget sulfur, because otherwise you can't get a real physical solution. The model is unable, if it arrives to solve numerically this region, it's unable to understand if you are here and here. And this is because there is a strict requirement that we should remember. When we talk about saturation of volatile components in a system like silicate, such as silicate melts, we can't say, like many do, sulfur will exsolve after water and carbon dioxide. When there is exsolution, all the volatile components must exsolve. This is a strict thermodynamic requirement, which means that at the saturation threshold, any model should be able to compute the simultaneous concentration, exsolution of carbon dioxide, water, and even if it's about a very tiny amount of sulfur, also about sulfur. And the point is that if such tiny amount is very tiny, then you have a numerical crash. And that's the problem, especially with oxidized sulfur. If you give me just a few more seconds, then this is the input about, for example, the way it's Fortran command line. It's not user-friendly. So this is the input file. There is also a driver file which gives you the instruction. One thing that this code can provide is the computation of oxygen fugacity from divalent and trivalent iron. For example, like in the Fuego example provided by the colleagues in New Zealand, by Harry, we have divalent and trivalent iron, so we can compute at any step during the compression, we can compute the oxidation states. And everything can be found in this short PDF. I repeat, I'm sorry, but it's not user-friendly, all this, it's command line, so you have to handle with that. And you just simply launch the exe file. This is for Windows. You get something like that. It starts with some iterations, the compressing, for example, from 200 MPa, 2000 bar. You see, there is a spike error in finding gas composition under saturated conditions. So now later on, we'll check if it has been able to solve this condition? Apparently, yes, because it appears just once, and then it goes down to 1800 bar and so on. I show you the final output. The final output is a file like this: pressure, temperature in Kelvin, dissolved water, dissolved CO2, dissolved sulfur, exsolved water, exsolved CO2, exsolved SO2, exsolved H2S, mass of the gas mass, volume of the gas phase, mass, weight fraction of S2 minus, weight fraction of sulfate, the ratio between them, which of course doesn't matter because it's about the atom. Because it's about the atoms, it doesn't matter, mass or molar is the same, it doesn't make any difference. So just to show you, of course, there are some nonlinear features which can come out. For example, this is the, let's remove this. Yeah. So this is okay. Or you can also, you see that there is an increase of the sulfur oxidation states with the compression. You see that there is also an increase of the, you have first a decrease of the oxidation state when you, the oxidation state of the relative oxygen fugacity with pressure, with decreasing pressure, then you have an increase. And many other things, of course, you can compute dissolved sulfur, CO2, dissolved CO2, whatever you want. There are many possibilities. Of course, iron is fixed because we have used the computation based on the bivalent and trivalent iron provided in input, and many other issues, such as, for example, the last one I want to show you, the H2S SO2 ratio in the gas phase. So again, there are some non-linear features. We think that they have a physical sense. If they are real, this could be a matter of discussion. Sometimes non-linear behavior emerge when we look at simple indicators, but linear behaviors related to the thermodynamics laws are there. It's just a matter of calibration, and calibration depends also, of course, on the model you set, the theory you set, and on the quality of the data, if trash in, trash out. I'm of course available for any other explanation or contribution. I must provide you some results. Sorry, this terrible week I couldn't provide the calculation, only this, but I will of course contribute very soon. Thanks for your time and patience.
Thank you, Roberto.